Hey guys, it's Off by 1 here, and today we're going to be solving counting bits. In this problem, we're given an integer n, and they want us to return an array answers of length n plus 1, such that for each element, the number of ones in the binary representation should be stored in that index. So what does that mean exactly? Well, let's take the number 3. In binary, this would be 1, 1. So for answers at 3, we would have to store a value of 2 because there's 2 ones there. So the full answers array would look something like this, where if we take this array for example, because it's not going to change, these all will have the same amount of ones no matter what the n is. So our array for this example would be 0, 1, 1, and 2. And we would return this whole array here at the end. Okay, so let's start by going over the brute force solution. So here I've initialized the example for n equals 3. And here I have the array going from 0 all the way to 3. And in each one of these indexes, we're going to put how many 1 bits there are for that number. So for example, for 0, we know there are 0 bits, so I'm just going to initialize it to that for now. And let's say we're at 1 now. Well, if we're at 1, we have to count how many 1 bits there are. And 1 in binary is still just 1, but we would have to have a nested for loop to be able to count how many 1s there are here. And that would take n time, so let's just do that. We have 1 bit for 1. What about for 2? Well, 2 now has 2 bits, 1 and 0. And we have to run a for loop through all of the bits to find out there's only 1 there. So we're going to store that. And then for 3, same thing. We're going to have 2 bits, but we will need a for loop to iterate through all the bits, and then we would be able to store 2, because we would find that there's 2 1 bits there. But the problem is that the time to run his algorithm would be O of n log n. The reason it's n log n is the n comes from iterating through this whole array, which is of size n, and the log n comes from iterating through the binary bits. And as you can see, we don't actually have as many bits as there are, let's say 3 for example. We don't have 3 bits here. We only have log n plus 1. So if we had 16, let's say, 16 in binary would be 1, 0, 0, 0, 0. And log base 2 of 16 is equal to 4. But you can see we have 5 bits here, so that's why it's plus 1. But all of this simplifies to just log n anyways, so that's why this is our runtime. And there's actually a more efficient solution that runs in just O of n time. So the only way to actually get an O of n time is by using dynamic programming. And what does that mean? Well, let's say we have this 0 here, and we have a 1 here. Well, to calculate 2, we should use one of these 2 indexes to calculate 2, instead of going through 2 as a binary bit and counting the ones individually. So I'm just going to fill these out, and then once I'm done with that, we can go over it and see if we notice some kind of relationship between the numbers. So the first thing I notice when solving this problem is the placement of these 1s. These 1s are all going to be in powers of 2. So for example, this one is in 2 to the power of 0, this one is in 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So basically, if we have a power of 2, then that means we're only going to have 1 bit. And if you think about it, let's say we have the number 32. Well, that would still only have 1 bit, as you can see here. So we have this 1 at the end, and then 0, 0, 0, 0, and 0, I believe. And no matter how big the number gets, there's still always going to be a 1 bit if it's a power of 2. Okay, well that's useful, I guess, but how can we use this to find the numbers that are not powers of 2, like these for example? Well, let's take 3. We know that 3 is made up of the 2-bit and the 1-bit in binary. So this would represent the 2 and this represent the 1. And this makes up 3. Okay, so maybe we can say that, let's say this array is called dp. dp of 3 could be equal to dp of 2 plus dp of 1. But what does this really tell us about the rest of the numbers? Well, let's see if it holds for 5. So dp of 5, what would that be? Well, we know that 5 in binary is going to be equal to 1, 0, and 1. This is the 4-bit, 2-bit, and 1-bit. So we can say that dp of 4 plus dp of 1 makes up 5. So what we're noticing here is that we're using the most significant bit and then just adding 1 to it. Okay, but we can also see that it doesn't hold true for 7. So for example, let's say dp of 7, we will make that equal to the most significant bit, which is currently 4, plus dp of 1. And as you can see, that does not equal 3 because dp of 4 is 1 and dp of 1 is 1. And that will give us 2. So what's the actual relationship here? Well, instead of dp of 1, we can say that this is instead dp of 7, which is our current iteration, minus the most significant bit, which is 4. And that will give us a dp of 3. And then this would equal 3, because dp of 4 is 1 and dp of 3 is 2. So 1 plus 2 would give us the 3 here at 7. And this also holds true for the previous examples. So for 5, we have dp of 4 plus dp of 5 minus 4, which would be dp of 1. And same thing for 3. So our pseudocode is going to be something like iterate through all of the array, and for each number in the array, we want to find the biggest power of 2. So we can just say find most significant bit, and I'll show you how to do that in the code. And then after that, you just want to do dp of I is equal to 1, because we know this is just going to be 1 at all times since it's the most significant bit. So we don't have to worry if it's 2, 4, 8, 16 or anything else, because they're always going to be 1. So that's why it's 1 here. And then we can do plus dp of I minus the most significant bit. And then at the end, we can just return our dp array since that's what it wants. It doesn't want it at a particular index. And that's our whole algorithm. Our time for this is going to be O of n, since we're only iterating through the array once. And the space is going to be O of n as well, because we have to store this array here. So now let's get into the code. So to start, I'm going to initialize the answers array, and it's going to be all zeros for a length of n plus 1. The reason it's n plus 1 is because we want to have room for our base case at 0. And then from here, I'm going to initialize a variable, and I'm going to call it largest bit. And we're going to use this to keep track of our most significant bit, like we said in the code. And I'm going to set that equal to 1 to start. And now we go through every single n. So for I, in range of 1 to n plus 1. The reason we start at 1 is because we already know that at 0 is going to be 0, so we don't need to calculate that. And then from here, we want to calculate our most significant bit. So how do we do that? Let's say our largest bit is 1 right now, so I'm going to write that down here. Largest bit is equal to 1. But let's say our I is equal to 2. So that means we're at the second iteration, and our most significant bit should be the 2's place. So what we want to do is check if largest bit times 2 is equal to the I, so the current iteration. Then we want to update our largest bit to be equal to I. And the reason we do this is because our I at this point, let's say I equals 2, that would be our new most significant bit, and that's why we update it like this. From here, we just want to do what we did in the pseudocode again. So answers at I is equal to 1 plus answers at I minus largest bit. And then that should fill in our array, and at the end, we just return our answers array, and that should work. So as you can see, this code is pretty efficient, and now I'll go through the code manually. So to start, the example we're going to be doing is n equals 5, and in our code, we initialize our answers array to be all zeros for a size of n plus 1. So as you can see, our answers array is a size n plus 1, and I only put this as a 0 for now because we're going to update the rest, so I don't want to make it too messy. And then our largest bit is going to be initialized to 1, which I've already done here. So these are checked off, and now we can go into our for loop. So for I in range of 1 all the way to n plus 1, then we want to check if our largest bit times 2 is equal to I. And like I said before, the reason we want to do that is because this is how we find our most significant bit. So let's see, largest bit is currently 1 times 2, well that equals 2, and I is 1 currently, so this is false. So all we want to do is update our answers array at I, which is 1, to 1 plus I minus largest bit, and this would be 0. So our answers at I would be equal to 1. And now we go to the next iteration. So now we're at I equals 2. And let's see, largest bit is still 1, but our I is now 2. So we want to update our largest bit to be equal to I, which is 2. Okay, so now we do answers at I equal 1 plus answers at I minus largest bit, and I equals 2. And our largest bit is also 2. So this would be answers at 0, which is 0, plus 1. So at our 2 spot here, we want to have a 1. And now we're at I equals 3. So largest bit is still going to be 2 times 2, that is equal to 4, so this condition is false. And then answers at 3 is equal to 1 plus answers at 3 minus 2, which is 1. So we would have 1 plus whatever's in the 1 index, so 1, and that would be 2. And now we're at I equals 4. So let's see, largest bit is 2, so 2 times 2 is equal to 4. So now we're going to update our largest bit to be 4. And then we update our answers at I, which is 4, to be equal to 1 plus answers at 4 minus 4, so this would be 0, which is also a 0 value, so we would just store a 1 at index 4. So now for our last iteration, we're at I equals 5. So we're going to have largest bit times 2, so 4 times 2, that's 8, so that's not equal to 5, so we can just ignore that. And now we update answers at 5 to be equal to 1 plus answers at I minus largest bit. I is 5, our largest bit is 4, and this would be equal to 1, and answers at 1 is 1. So we would update 5 to be equal to 2. And that's correct. If this video helped in any way, please leave a like and subscribe. Thanks for watching, and I'll see you in the next video.